This is an introduction to Lab 2, Kepler's third law. And before you can actually get started with the calculations, you need a few more data, and I do this on purpose so that you can see where those data actually are coming from. So we're looking at Jupiter through a telescope here, and we see the 4 large moons, and in the real sky they don't have names attached to them. We would have to figure out which is which on our own, but it just makes it a little bit easier here for me while I'm recording this. We have already data given for Io and Europa, which are 3.5 days for Europa and 1.77 days, pretty much exactly half of that for Io. So we have to figure out Ganymede and Callisto. First, we're gonna figure where they start out. Callisto is about a Jupiter diameter to the right, while Ganymede starts out almost at the edge of the frame. And now I'm gonna give you a picture every 6 hours, and we notice which direction they move. Ganymede actually moves left, Callisto moves to the right. So we go through the motions here. Of course, Ganymede is back in the same spot, but obviously it hasn't orbited yet. So we keep on going. We don't actually have to pay attention to Callisto for a while because it takes a long time to orbit. So we just focus on Ganymede for now. And so it's coming back. It's going to be almost there. And let's see. Yep, about there. So that's pretty much 7 days and 6 hours, so keep that in mind. 7.25. That's a rounded number. Callisto is coming back. Of course, it's not there, respectively here. It's about a diameter away, but it's on the other side of Jupiter. It hasn't definitely not completed an orbit, so we have to keep on going with Callisto. All the way here, you see quite a dance of the moons around Jupiter. Okay, there comes Callisto now. It's in front of Jupiter now. And that's about right. So we have your 16 days and 18 hours, or 16.75 days. So that's what we'll be entering in the table. So here you would actually have to enter those data. So we said 7.25 days for Ganymede and 16.75 days for Callisto. And now we need to make the calculations over here. So we need to be looking at the numbers that we need here and plug them in according to p squared over a cubed. So period is 1.77 days, distance is 5.91, and that is in the units of Jupiter radii. So Io is 6 times, almost 6 times as far away as what the radius is of Jupiter. Europa has a period of 3.55, and it has a distance of 9.4 Jupiter radii. And now I'm going to go over to a calculator. Of course, you can use any kind of calculator you want. I'm just going to use this one here because it's nice to show on this one here when I want to teach. So 1.77 squared divide by 5.91 cubed. And of course, we have that number already given there, 0.0152 rounded, but I just want to confirm that that's what we come up with. 3.55 squared for Europa divided by 9.40 cubed, and we're going to come up with 0.0152 rounded, and so on for the other data. Let's look at Saturn. Well, the same thing will happen. So we have 16 squared divided by 20.3 cubed, and it's a 0.3060. And then we have 0.94 squared divided by 3.1 cubed, and we come up with 0.297 rounded. Looks a little bit different, but notice that we only have two significant figures here given, two digits on a 3.1, so our result is going to be a little bit inaccurate, but still the two are close that we can call them virtually the same, and that is what Kepler's third law is saying, which is what you should get out of this lab here, that Kepler's third law applies to any moons as they're orbiting their planet and has to be obeyed by anything that is orbiting. And now let's go on to Uranus, but here we have to still get some more data, so I'm gonna go back to my software. Here we're looking at Uranus and three of its moons, Umbriel, Miranda, and Oberon. We already got the data for Miranda, so let's look at Umbriel and Oberon. Umbriel above, Oberon below. And our date would be January 8th, 1 in the afternoon. I chose that because I finally got them both in the same picture here. Umbriel is going to be the faster one, so let's look at it first. Oberon went down, so did actually Umbriel, so they both went down behind the planet. Notice that it's actually turned by 90 degrees. The reason is that Uranus lies on its axis and the moons orbit in the same way that Uranus is turning. So maybe a little bit ahead of this one here. So we started on the 8th, so we have 4 days, 4.25. So let's round it down to 4.1 because it's a little bit before this. So 4.1 days on this one. And let's look at what happened to Oberon. Because it went down at this point, it has not completed an orbit. It has to go up first. Of course, I'm clicking so fast that the other two are really zipping along here. Okay, that's pretty good actually. So on the 22nd at 1 in the afternoon, which makes it pretty much 14 days. Actually, I'm going to correct myself. That's not 14 days because we started at 1 in the afternoon, 13 hours. So this is 13 and a half days. We also need to figure out what the distance is of Oberon, so I'm going to click on it, and you could get this information from anywhere. I'll look it up right here. And it says 0.58 million kilometers from Uranus, so 580,000 kilometers from Uranus. So here we're going to put in the data, so it's 4.1 days for Umbriel, 13.5 days for Oberon, and we had 580,000 days for Oberon's distance, not 580,000 kilometers, of course. And now again we're going to plug in the numbers. So for Miranda we're going to have 1.41 squared, 1.41 squared divided by 130,000 cubed, and we end up with 9.05 times 10 to the negative 16. It's of course rounded. And for Umbriel we're going to have 4.1 squared divided by 266,000 cubed, 8.93 times 10 to the negative 16. Again, the slight discrepancy here is that some of our numbers were rounded to begin with. And that should be good enough for an introduction to this Lab 2 on Kepler's third law.